Welcome to ES 310 Lesson 14. Today we're going to continue the material that we started in Lesson 13 on the impulse momentum method for solving kinetic problems. We are going to focus in on a special situation where we have non-impulsive forces, which will allow us to use the conservation of momentum. We will be looking at systems involving multiple particles that collide today. For more information on these topics, please see Hibbler's Dynamics Text, Chapter 15, Section 3. By way of motivation, let us take a look at a quick video. So all of those tricks involved with those balls have to do with conservation of momentum, which is what we will be learning about today. So keep those tricks in mind as we cover the content for today. So the first thing we need to talk about is the difference between impulsive and non-impulsive forces. An impulsive force causes an impulse. So like we saw yesterday, impulse is equal to the integral of a force dt. Right? So if a force causes an impulse, then it is an impulsive force, and the things that we're going to learn about today, conservation of momentum, does not apply. If it doesn't cause an impulse, then it's a non-impulsive force, and we can use conservation of momentum. So the question is, in which cases would a force not cause an impulse? If the force is very small or the time is very small, you wouldn't necessarily get an impulse from that force. So ask yourself, does this force cause a change in momentum of my system? If a force is much smaller than other forces, so for example, when you hit a ball with a tennis racket, the force that the tennis racket applies on the ball causes an impulse. Right? It changes the momentum substantially. The weight of that ball is also a force acting on the ball over a given time. That weight is so much smaller than the force of the tennis racket that the weight is non-impulsive, so we can ignore that weight. So in the situation where we have non-impulsive forces, we can take a look at our principle of impulse and momentum from last time, and we can simplify that. So if we have non-impulsive forces, this side of the equation goes to zero, right? There's no impulse. If that's true, then the momentum before is equal to the momentum after, or conservation of momentum. This is particularly helpful when we're dealing with sets of particles, right? So if we add up the momentums of all of the particles in our system before the impact, that's going to equal to the momentum of all the particles in our system after the impact. So if we have two balls, for example, and they're rolling towards each other, each of them has a momentum, they hit, bounce off of each other, they each have momentum afterwards. The sum of those two momentums is conserved, right? They're equal. To derive this, if we have ball A, right, it's going to have an impact. So there is a force that's causing a change in momentum, right? The force of one ball hitting the other, right? So that impulse is equal to the change in momentum. Ball B, same impact, right? These forces are equal and opposite because they're hitting each other, equal to change in momentum. If we add them together for the whole system, we get the impulses, which cancel out, one's positive and one's negative, is equal to this sum of momentums. And we can move the initials to one side, the ones, the finals to the other side, and you have your conservation of momentum. The procedure for this method, which is typically applied when we're asked to find velocities for various particles in a system of particles before or after some sort of impact occurs. So our procedure is we establish a coordinate system as usual. We check for applicability, which means we need to have no external forces or only non-impulsive forces, right? This is external to the system. So when the two balls hit each other, those are internal forces because they're internal to the system and they cancel out. We establish our x and y components for the initial and final velocities. Some of those will be unknown, so we can assume a positive direction if they're unknown. And then we apply our impulse momentum or our conservation of linear momentum, depending on whether or not we have impulsive forces. We solve for our unknown velocities, and if we need to, we can then back out the force acting on a given particle if we separate it from the system. So let's take a look at an example of this. We have two blocks. Block A is sitting still and is sitting up against this spring, which is currently unstretched. Block B is sliding along the floor. There's no friction. It starts sliding at 15 meters per second. It hits A, and they both then slide a little bit further and compress the spring. And the question is, what is the compression of the spring? So there's two parts to this problem. First, there's conservation of momentum, right? Because there are no external forces that are causing an impulse, that are causing a change in momentum. The only change in momentum is going to be caused by B hitting A, which is internal to our system. So first we're going to use conservation of momentum. Then we're going to use conservation of energy because we have to deal with this spring. So let's start with conservation of momentum. Conservation of momentum says that ma va1 plus mb vb1 is equal to ma va2 plus mb vb2, right? So our initial momentum is equal to our final momentum. Initially, block A is not moving, so that's 0. Block B has a mass of 10 and is moving at 15 meters per second. Finally, they get hooked together and they're moving together, right? So their masses get added and they have the same velocity. And we'll just call it V. All right, because they're moving together, so VA2 is equal to VB2. So sum of the masses, 10 plus 15 times V, the only unknown is V, so V, our final velocity of the moving together, is equal to 6 meters per second in that direction. Alright, so now that we have the final velocity, now we're going to move into the conservation of energy section, right? So this is, think back to last chapter, we've got something moving initially and there's no potential energy. And eventually it comes to rest, so there's no kinetic energy, but there is potential energy because we've compressed the spring. So we have T1 plus V1 is equal to T2 plus V2. There's no gravitational potential energy involved because we're staying horizontal. So initially we're moving, so we have 1/2 m, and in our case the two m's are moving together, so it's ma plus mb. Times v squared, where this is v up here, the 6, is equal to, so this is 1/2 of 25 times 6 squared. And on the other side, we're going to compress the spring to some amount, right? We're going to move to there. So the kinetic energy is going to be 0. This potential energy was 0. This kinetic energy is 0. All right, and then our potential energy is going to be stored by the spring, so 1/2 ks squared. And k was given as 10,000. So we have 1/2 of 25 times 6 squared is equal to 1/2 of 10,000 s squared. We can solve for s, and we get s is equal to 0.3 meters. So the spring compresses 0.3 meters. Here's another example, and in this example we're given information about relative speeds. So think back to our kinematics and how we deal with relative speeds, because we're going to have to deal with those in order to handle this problem. So what's happening here, we have a cart. Originally everything is stationary, all right? And then the boy and the girl start walking towards each other. The boy weighs 80 pounds, the girl weighs 60 pounds. The boy is moving at 3 feet per second, and the girl is moving in the opposite direction at 2 feet per second. But it tells us that those velocities are measured relative to the cart. So these are relative velocities. And then the question is, as they do this, the cart itself is going to start moving to conserve momentum, and we want to figure out what is the speed of the cart. So conservation of momentum, we'll start with that equation, right, tells us originally everything's stationary, so there is no momentum. Then everybody starts moving, so we've got the mass of the boy times the speed of the boy, plus the mass of the girl times the speed of the girl, plus the mass of the cart times the speed of the cart. That is our momentum. That has to equal to 0. So remember, momentum is vectors, so some of these are going to be to the right, some of these are going to be to the left. They're going to cancel each other out and be equal to 0. The kinematics is going to allow us to fill in some of these unknowns. All right, we know all the masses. The mass of the boy is 80 divided by 32.2. The mass of the girl is 60 divided by 32.2, and the mass of the cart is 300 divided by 32.2. All right, so kinematics, we get back to these relative velocities. So the velocity of the boy relative to the cart is equal to 3 feet per second to the right. So we're going to call the right positive. That's the convention. So we have 3 is equal to velocity of a boy relative to the cart is the velocity of the boy minus the velocity of the cart. The velocity of the girl relative to the cart is 2 to the left, so that's -2 is equal to the velocity of the girl minus the velocity of the cart. So now we have 3 equations and 3 unknowns right here. 3 equations, 3 unknowns. So we can solve them. So let's solve this one for VB, this one for VG, plug them in up there, and you'll have an expression for only VC. So we get 0 is equal to mass of the boy times 3 plus VC, plus mass of the girl times VC minus 2, plus mass of the cart times VC. And we only have VC in there then, so we get VC is equal to -0.27 feet per second. So as the kids move towards each other, the whole cart will move this direction. So the cart will actually roll while the kids are moving on it.